Hello students, today's topic is how the current varies in an electrical circuit when a capacitor and a conductor and also a resistance is included in the circuit. Here inductance L we are including, capacitor we are also including, resistance also we are including, then we call it as a LCR circuit. Before we proceed, what is resistance, what is conductance, what is capacitance, first we will discuss briefly. So, for DC we use resistance as a controlling current controller, but when you come to the AC we use what is called capacitor and inductance as the current controlling systems. But in case of this, if you use 3, then we call it as the total controlling is known as what is called impedance. So, the impedance consists of a resistance, a inductance and a capacitors. Similarly, if you use only a capacitor and a resistance, then it is called inductive capacitor reactance. Suppose if you use a resistance and a capacitor, then it is known as what is called capacitive reactance. Now, if you use in a AC circuit or a DC circuit as a capacitor and a resistance, how the current will grow, how the current will decay, that we will discuss in this chapter particularly. That is what you call it as the decay and growth of the current when L and C are used. Let us first discuss how the current varies when a capacitor and a resistance is included, and next we will discuss how the current decay and as well as is equal to grow when you use a resistance as well as the inductance. So, today's topic is this one. Now, as shown in the circuit diagram, battery is connected to a resistance and a capacitor and a Morse key, that is a two-way key. As shown in the circuit diagram here, in this case, so the capacitor is connected to a resistance is connected to the positive terminal of the battery and the negative terminal is connected to the terminal A. Now, if we connect K to the terminal B, then what will happen? The battery is included in the circuit. When the battery is included in the circuit, current will flow across the resistance as well as the capacitance. As the current flows through the capacitor gets charged. After getting charged, what it will happen? The capacitor will have the property of giving the back EMF. This back EMF will reduce the potential across the resistance. So, after some time what will happen? A equilibrium is reached and then the capacitor, the back EMF and the resistance will reinforce each other and we will get a growth of current as shown in the circuit diagram in this case. So, according to the formula for the current, if Q is the charge and Q naught is the charge before including in the circuit, that at any instant of time the capacitance across this one is equal, across the resistance is given by E is equal to Q by C is equal to R I. E is known as the voltage, Q by C is the voltage across the capacitor and R I is the voltage that is developed across the resistance. So, from E minus Q by C is equal to R I. So, by definition E is equal to dQ by dt, that the maximum charge path will be given by, in the next equation what we will get is equal to how much? Q naught is equal to C E, Q naught by C is equal to E, or Q naught by C minus Q by C is equal to R dQ by dt. So, Q naught minus Q by C is equal to R dQ by how much? dt. So, from this equation if you integrate, then you will get another property of the solution of this one is equal to how much? dt by C R is equal to dQ divided by dQ minus Q. Integrating above equation, what will get is equal to how much? T divided by C R is equal to minus log E Q naught minus Q plus A. A is known as the integration constant. In order to find the value of A, we apply certain boundary conditions. The conditions given by the equation is equal to, when t is equal to 0, q is equal to 0, therefore 0 is equal to, we will get this value. So, A is equal to log to the base e q naught. Substituting this value, T by C r is equal to minus log e q naught minus q plus log e to the q. So, minus T by C r is equal to log to the base e q naught minus q minus log e q naught. If you simplify this equation, finally we will get log to the base e is equal to q naught minus q by q naught, or taking the exponential on this equation is equal to e to the power of minus t by C r is equal to q naught minus q by q, or that is equal to how much, 1 by q minus q naught. So, on that basis, q by q naught is equal to 1 minus e to the power of minus t by C r, or q is equal to q naught into 1 minus e to the power of t by C r. Here t is known as the time constant. So, that means this is an exponential term. As the time increases, the growth of the current will also increases and reaches to the maximum value. So, suppose if we substitute this value of t is equal to C r, then the equation is finally turns into t is equal to C r, q is equal to q naught 1 minus e to the power of minus C r by C r, q naught into 1 minus e to the power of minus 1. So, q is equal to 1 minus 1 by e, or q naught is equal to this much. Then what will get, finally value is equal to how much, 0.63 q naught. This time is known as the time constant of the CR circuit, which means when that is the time at which the total charge will be 0.63 times that of the original charge. This time is known as the time constant. So, now if you draw a graph between the time and the charge what you have measured, you will get a growth current as shown in the diagram. So, this diagram is equal to how much he will get the growth of the current. The same thing which we can explain the above result in the form of a simple experiment. So far we have discussed about the growth and the decay of current in a CR circuit. So, in the CR circuit particularly when the capacitor gets charged, back EMF will prevail. So, due to which there is a fall of voltage across the resistance. So, to show this one, we have the following circuit which is given in the circuit number 1, which is connected here 6-volt battery, then it is connected to a resistance and a capacitance, and the circuit is closed. In certain cases we use charge and discharge keys. Here I am not including the charge and discharge keys, only I am showing how the voltage back EMF is prevailing on the resistance. For that, so battery is connected to the resistance and the resistance connected to the capacitance. As the current flows, the capacitor slowly gets charged. After some time, it will give the back EMF. Due to this back EMF which is in opposite direction, there is a voltage developed across the resistance. Now, we will measure the voltage, how the discharge increase of voltage is taking place with respect to time, how decrease of voltage is taking with respect to time. One is for growth of the current, another is for the decay of the current. This can be demonstrated with a simple experiment as shown here. This is your battery, what we are having a 6-volt battery. This 6-volt battery, the positive terminal of the 6-volt battery is connected to a resistance box. Here we are including a resistance box. Instead of resistance box, we can use a resistance, common resistance also. The other end of the resistance is connected to the other end of the capacitor, and then it is connected to the negative terminal of the battery. In this way, as shown in the circuit diagram, the circuit is completed. So, though as we put the key here, charge here, the current begins to flow into the capacitor and the capacitor gets charged and it gives the back EMF. Thereby, what is the voltage across the input voltage, how much, what is the capacitor voltage is how much, how this capacitor is falling, that we can find out this one. So, now this is the voltage across the battery. What is the input voltage? If you see in the voltmeter, this is the voltmeter both which is can be measured for AC voltage as well as the DC voltage. So, as likewise we measure the voltage across the battery, this voltage input voltage is about 6 volts. Then this same voltage we can measure across the capacitors. So, that means means that the two terminals are connected to the capacitor in this way. So, on connecting this one, there is a voltage across the capacitor also. So, that means the capacitor gets charged. So, when it gets charged, after some time it reaches to a maximum value, after which it attains the maximum value, there will not be any further increase in this one. Now, if you measure the voltage across the resistance, which we have shown in the form of a resistance box, then as the time increases, there is a slow decrease in the current will take place, thereby we will have what is called a growth of current will take place in the first case. Then we include this what is equal to in the second case, we disconnect the battery. Once again, when we disconnect the battery, the charge that is already present in the capacitor begins to get discharged, and thereby there is a fall of current. So, but fall of current is equal to how much here? Once again, there is with respect to time, after some time there is a considerable fall of current, and it reaches to the what is called exponential curve. So, in one case the charging will be there is an increase of current, in other case there is a fall of current, there is a what is called is equal to how much? Decay of the current. From this formula, I is equal to I naught e to the power of minus t by RC, from which we can calculate the time constant of the CR circuit. So, after this, the same thing we that time constant of the circuit will be given is equal to how much? I is equal to I naught e to the power of minus t by CR. When CR is equal to t, then it will become how much? I by I naught is equal to e to the power of minus 1, or e to the power of minus 1 is equal to 1 by e, from which it will be equal to how much? 0.3 it will become how much? About 0.37 times that of the total voltage. So, this total voltage means in a particular time where the current reaches the maximum value or the voltage reaches the maximum value can be calculated from the CR growth circuit. So, similarly, while increasing this is equal to, in the case of decreasing also we are having another formula, I is equal to I naught into 1 minus e to the power of minus t by CR, from which one also we can calculate. In that case, the current value or the voltage value will be 0.63 times the original value. So, both the what is called the growth and the decay of the current can be found out from the CR circuit. Here the only apparatus we have to use is equal to a simple capacitor, a 6 volts battery, or even a less volt battery, and a voltmeter to measure the volt. Instead of voltmeter, we can use a ammeter also to measure the current also. So, either you can measure the current across the either you can convert in terms of the current, or you can convert in terms of voltage, from which we can get both the growth and the decay of the current in the case of CR circuit. Next, we will proceed for the next type of circuit, that is called what is called LR circuit. Here, as shown in the LR circuit, here if you see this one, so this is E is the terminal of the E is the what is called is equal to how much? The terminal of the battery, source of the battery, R is the resistance here, L is the inductance. So, E is connected to the resistance, L is connected to the other end of the resistance is connected to L, and then it is connected to the what is called is equal to common terminal Morse key K. So, now if we connect this key to B, what will happen? The battery is included in the circuit. If you connect this one to the terminal A, the battery is excluded. So, when you connect it to the B, what will happen? The battery is included and the current will flow in the circuit. Thus, flow of current will give the growth of the current in case of LR circuit. If you connect this one is equal to how much here? Since you have removed the battery, there is a what is called decay in the current. So, what will happen? This will give without the battery, and the what is decay of the current means charging of the inductance will take place. Because of the charging the inductance, there is a slowly decrease in the current. How it will decrease with the time, what is the time required, all those things we can calculate in the subsequent equations. As shown in the circuit diagram here, now if a particular instant of time, if you give all the connections here, the current start flowing through the circuit, the resistance across the resistance, and then across the what is called inductance L. As the current grows in the inductance gets charged, and this inductance after getting sufficiently charged, it begins to get discharged and gives the back EMF. So, the back, so at any instant of time, the voltage that is dropped across the what is called resistance is given by the EMF of the cell, that is E minus L di by dt is equal to how much? Ri. So, if you substitute this equation, rearrange this equation here, di divided by E minus Ri is equal to dt divided by L. So, multiplying both the side by R, that is equal to minus R. If you multiply R into di by dt is equal to E minus Ri, that is equal to minus R dt by dl. So, this will become here the differential coefficient of the denominator, it happens to the numerator. Therefore, the integration of this function is log of the denominator, which is given by log E minus Ri is equal to minus R divided by L into t plus A, where A is known as the integration constant. As we have done in the case of CR circuit also, here you have to find the value of A. In order to find the value of A, the boundary conditions is to be applied. For applying the boundary conditions, we apply here when A is equal to how much? When t is equal to 0, there is, when starting time there is no current is flowing into the circuit. Therefore, when t is equal to 0, I is equal to 0, and hence log e to the base e is equal to 0 plus A, thereby we will get A is equal to log e to the base e. Now, if you substitute the value of this one here, log e to the base e minus Ri is equal to minus R by L into t plus log e to the base e. Therefore, log e minus Ri by e is equal to this much. So, now if we integrate these expressions here, what we will get is equal to E minus Ri is equal to e to the power of exponential of minus RL by t, that is equal to 1 minus R. Rearranging the terms, we will get is equal to 1 minus Re by E, that is equal to e to the power of minus RL by t. So, Re is equal to 1 minus e to the power of minus R by L into t, Ri is equal to E by R will be this one. So, this is the value, current value will obtain in the case of LR circuit. The maximum current in the circuit will be when I naught is equal to E by R. So, I is equal to I naught E 1 minus e to the power of minus RL divided by t. So, this equation represent the circuit at any instant. This gives the equation, that is the current at any instant of time in the LR circuit. So, therefore, the current that is flowing through the choke at any time is given by I is equal to I naught e to the power of into 1 minus e to the power of minus RL by t. Here another important point we have to remember, what is the time constant of the LR circuit. To find the time constant of this LR circuit, what you use here, t is equal to, instead of R by L is equal to, if I say L by R, then L by R into R by L get cancelled, then what we will get is equal to, here in the equation here exponential minus RL by t is equal to 0 and t is equal to how much? Infinity. Here in this case, therefore, what will happen is equal to how much? E to the power of 1 by e to the power of 1 minus 1 by e to the 1 by e, but 1 by e is equal to how much? 2.178. If you calculate this one, they simplify this equation, what will get is equal to 0.63 I naught. So, this is the time constant which we can calculate when the current is flowing through the LR circuit. Here we define the what is called time constant of circuit in this way, is the time at which the current, the total current in the circuit will be 0.63 times that of the I naught, that is at t is equal to how much? R by L. From this equation, now if you draw a graph between what is current I and in the time t, a growth current will be there. Further, if you differentiate this fraction, what will reach a rate of decay of the current also we obtain. But this rate of decay current we show di by dt is equal to, if you differentiate this above equation and following the steps here, di by dt is equal to I naught R by L, I naught minus I divided by I. Therefore, R by L is equal to I naught I. Suppose if I is equal to I naught, this expression becomes infinity, which means the current can never be equal to that of the original current in the circuit. So, in this way, if you draw a graph from this one, we will get a growth of the current in case of LR circuit. Now, after that, when we go back to again in the original circuit here, So, in this case now I will exclude the battery. In order to exclude the battery, this terminal K is connected to the terminal A, only R and L will be there. Here all begins to discharge, and then the current will measure the voltage across the resistance. Subsequently, we will measure the current across this one during the process of decay. So, in that case, the voltage across the resistance at any time is given by minus L di by dt, that is equal to Ri, that is equal to how much? If you substitute di by dt is equal to minus RL by dt. So, now if we go for this one is equal to, here further simplifying, this is equal to log integration of this function will get log I to the base e is equal to minus RL divided by t plus b, where b is known as integration constant. In order to find the value of b, if we apply the boundary condition, that is when t is equal to 0, I is equal to I naught, it will become how much? Log to the base e I naught is equal to b. Substituting these values, we will finally obtain the equation which is given by log to the base e I by I naught is equal to minus RL divided by t. So, here also we can calculate the time constant during the process of decay of the circuit. So, for that I apply equation is equal to how much? When t is equal to R by L by R, if I write it, that is lambda is the time constant. If you assume that one L is lambda is equal to L by R, then this will become inductive time constant. This constant, if you substitute the value, what will get is equal to how much? E to the power of I is equal to I naught e to the power of minus R by L, that is equal to e to the power of minus 1, and hence that is equal to I is equal to I naught by E. The value of E is equal to 1 by 1 divided by 2.718, then we will get is equal to how much? 0.370, which means the total current at any time in the LR circuit is given by 0.37 times to the power of I to the original current. Therefore, the time constant of the circuit can be defined as the time taken by the growth or decay of the current when the current value becomes, when the time value becomes how much? Equal to how much? L by R. So, this kind is known as the what is called the time constant of the decay circuit, LR circuit. Finally, now if you draw a graph between the LR circuit in this one is equal to, we will get a similar type of graph as I have got in the case of what is resistance, in the case of what is called capacitive reactance also. So, that is also in the decay of process you will have the same type of graph as we have shown in the case of this one is equal to. So, there is a decrease, this is a growth of the current, then we have the decrease of the current. In that case, this is the decay of the current here. This here what will happen, as the time increases, the what will happen, there is a decrease in the current value, and this graph will give you what is called is equal to how much? Decay current in the LR circuit, decay time of the CR circuit. Decay time of the CR circuit is given by here as in the circuit Q is equal to Q naught e to the power of minus 1, or that is equal to Q is equal to e to the power of E, or that is equal to Q naught is equal to 2.718, which is equal to 0.37 Q naught. So, 0.37 Q naught time is the time taken for a CR circuit when its current becomes 0.37 times that of the original current. Now, we discuss about the LR circuit, how the current growth and decay will take place in LR circuit in the practical aspect. The same circuit diagram, as shown in the circuit diagram, we are having a battery 6 volt battery which is connected to the resistance and a inductance L. So, as the current flows through this one, the inductance gets charged and a back EMF also will take place in the case of LR circuit. The same circuit I will show in the form of experiment here, what we will do generally for finding the growth and decay of the current in the circuit. As shown in here, we are having a 6 volt battery, a DC battery, then it is connected to a resistance box. The other end of the resistance box is connected to a inductance. The inductance means generally what we use in the form of a choke. The other end of the choke is connected to the negative terminal of the battery. Here I have not included the battery, the switch on switch off key, only we are interested in showing how the current will grow, how the current will decay in the case of LR circuit. For example, if you after giving this connection, now the input voltage what you are giving across the battery is equal to how much, about, if you connect these two things with the help of this voltmeter, the voltmeter is always connected in parallel with the battery. The voltage shown in the voltmeter, which is a AC or a DC voltmeter, here it is a combined one, the input voltage is about 6 volts. So, that means we are giving 6 voltage 6 volts current to the LR circuit. So, due to this current, how much voltage is that is developed across the resistance? Here I am connecting the resistance box also. I have taken pluck out about 100 ohms in the resistance box. Then there is a voltage across the resistance box also. This voltage we measure here. Then what is the voltage across the inductance, that also we can see from this one also. So, that means we are giving 6 volts input to this one, that when they come to the resistance there is some voltage here. In the case of choke there is some other resistance. As the time grows, the back EMF will be there, the resistance across the voltage across the resistance constantly, what will happen is equal to how much first it will grow and reaches to a maximum value. Later on the back EMF will take place, due to which there is a fall of current, that we can see in the case of by varying the resistance value, and you can measure the voltage across this is equal to voltage across the inductance. So, inductance voltage is given by here minus L di by dat. So, minus L di by dt will give the voltage, Ri is the voltage across the resistance, but the formula we are having is equal to, according to the Ohm's law, E minus L di by dt is equal to IR. Like that, as this voltage changes, as the resistance changes, voltage is also changes. From this we can draw a curve both for the what is called growth as well as the decay current in case of LR circuit. So, these LR circuits and CR circuit generally we use for filters. In case of converting the filters, here we are having AC. To convert is equal to how much here, AC current into DC, we need to reduce the ripples. For reducing the ripples, what you use the filter circuit. These filter circuits are known as LR circuit and CR circuit. This LR circuit and CR circuit very helpful in finding in reducing the ripples of the when AC is converted into DC, that is what is called is equal to how much, rectifier. Another point is, instead of using R and capacitance is known as the reactive capacitance, and R and inductance is known as the inductive reactance. Suppose if we use only R and L and C, then it is known as LC circuit. The LC circuit having a special feature, that special feature is an oscillating circuit.